Now, let us discuss the example 4.9 to illustrate the biasing schemes discussed earlier. In this problem, it is required to design the circuit shown in this figure to establish a DC drain current of 0.5 milliampere. The MOSFET is specified to have the threshold voltage Vt of 1 volt and Kn-W by L equals 1 milliampere per volt square. For simplicity, we can neglect the channel length modulation effect, that is, we can assume lambda as 0. The power supply is given as VDD equals 15 volts. In this problem, we need to calculate the percentage change in the value of drain current obtained when the MOSFET is replaced with another MOSFET having the same Kn-W by L but with threshold voltage as 1.5 volt. The given circuit is as shown here. So design meaning is we should calculate the values of RD, RS, RG1 and RG2. The data given can be rewritten as ID equals 0.5 milliampere, threshold voltage is 1 volt, the supply voltage VDD equals 15 volt, K-W by L equals 1 milliampere per volt square. The circuit is redrawn again. Now, there is a rule of thumb for designing classical biasing circuit. As per the rule of thumb, the voltage, supply voltage divides equally across various components. For example, in this example circuit, we have RD and a MOSFET. Supply voltage is 10 volt. Due to that, the 10 volts divides equally across RD and as well as MOSFET. The drop across RD is 5 volt. The drop across the MOSFET is 5 volt. The same rule can be applied even to this example. Supply voltage given here is 15 volt. Therefore, there are three components here: RD, MOSFET, RS respectively. The 15 volts here divides equally across three components. The drop across RD is 5 volt. The drop across transistor, saturated transistor, is 5 volt. The drop across RS is 5 volt. This rule is called as rule of thumb. Now for the given problem, VD is 10 volt. The voltage at the drain is sum of the voltage drop across the MOSFET and voltage drop across RS. VD equals 10 volt. Voltage at the source is 5 volt. Therefore, we can consider the ID required is given in the problem is 0.5 milliampere. The RD can be derived using this equation. The RD can be obtained by applying the KVL to the portion of the circuit. The part of the circuit is as shown here with VDD, RD and VD. If we apply KVL to this, we get minus VDD plus ID times RD plus VD equals to 0. RD equals VDD minus VD divided by ID. Now substituting the values of VDD, VD and ID, we get RD as 10 kilo ohm. Now to obtain RS, let us again consider the part of the circuit. Here the source voltage is 5 volt by the rule of thumb. Another end of RS is grounded. Therefore, RS equals Vs by ID. The same equation also can be obtained by applying Kirchhoff voltage law to this part of the circuit. Now by substituting Vs and ID, we get RS as 10 kilo ohm. Next, let us find the overdrive voltage. The overdrive voltage VGS can be determined by considering the drain current equation in saturation. The drain current equation in saturation is half Kn dash W by VOV square. Substituting the value of ID, Kn dash W by VOV can be obtained. The overdrive voltage on simplification gives 1 volt. Once we know overdrive voltage, we can calculate gate to source voltage using equation VGS equals VOV plus VT. The overdrive voltage is 1 volt. Threshold voltage of the MOSFET is 1 volt. Therefore, gate to source voltage is 2 volt. Now, to obtain the gate voltage, we know that source voltage is 5 volt. Then VGS equals VG minus VS, or gate voltage equals VGS plus VS. VGS is known, VS is known. We can calculate voltage at the gate. The voltage at the gate terminal is 7 volt. To establish VG as 7 volt, we can select RG1 as 8 mega ohm and RG2 as 7 mega ohm by trial and error method. Now we can write the original circuit and substitute all the values that we have obtained. VDD given is 15 volt, ID is 0.5 milliampere, RD that we have estimated is 10 kilo ohm, VD and VS by the thumb rule is 10 volts and 5 volts respectively. RS is 10 kilo ohm that we estimated. Now voltage at the gate is 7 volt. VG minus VT is 6 volt. The VG minus VT helps us to calculate voltage swing at the output. The DC voltage at the drain terminal is 10 volt. Therefore, the DC voltage for the amplified signal at the output is 10 volt. Now to calculate maximum positive swing and negative swing, we can use the appropriate equations. The DC voltage gain at the drain is 10 volt. The positive signal swing can be calculated by looking at the maximum positive signal excursion that takes. A maximum positive signal that can go up to VDD. Therefore, the positive signal swing is 5 volt that we can obtain by subtracting 15 minus 10 volts. Similarly, the negative swing at the drain point can be estimated by using the equation Vg minus Vt. The negative swing can excursion takes place up to Vg minus Vt. The Vg minus Vt value already we computed is 6 volts. Therefore, the negative swing can go up to 6 volt. The maximum negative signal swing now can be obtained is 10 volts and 6 volts. 6 minus 10 gives you the minus 4 volt. So the maximum negative swing is minus 4 volt. The maximum positive swing is plus 5 volt. Now, if NMOS is replaced by another MOSFET having Vt as 1.5 volt and same Kn dash into W by L, we can derive the other alternative values. The drain current equation, saturation drain current equation is given by ID equals half mu1 COX times W by L into VGS minus VT whole square. Substituting the values of ID that we need to estimate, substituting the values of mu1 COX, VGS is unknown, VT is given as 1.5 volt, the threshold voltage has been increased. Let us call this as equation 1. We know that Vg is equal to VGS plus ID times Rs. Substituting Vg and Rs is since 10 kilo ohm, the last or second term can be written as 10 times ID. Let us call this as equation 2. Equation 1 and 2 can be solved and we can obtain the values of drain current. Solving 1 and 2, gives drain current as 0.455 milliampere. Now you can see that change in drain current delta ID due to the change in threshold voltage is 0.455 milliampere minus zero point 0.5 milliampere, which is equivalent to minus 0.045 milliampere. Now to check the stability, delta ID by ID can be computed. On computation of delta ID by ID, which is minus 0.455 by zero point 0.5 milliampere into 100, that gives us minus 9%. This shows that the circuit is stable.